So let's look at recurrent neural networks now. We share the slides. So recurrent neural networks, as I already mentioned, humans don't start their thinking from scratch every other second. So thoughts have persistence. So when you deal with sequences, persistence of what I've seen in the past is an interesting aspect. So for example, when you are looking at the happenings in a movie, what is being shown at a moment will depend on the previous context, right? So recurrent neural networks addresses this issue, addresses the notion of persistence, which is relevant in the context of sequence modeling. So this is recurrent neural networks is essentially a deep learning model, which is used to model sequence learning problems. Right, sequence learning problems can be sequence to vector predictions, sequence to scalar predictions, sequence to sequence predictions, and things of that kind. So essentially, like it deals with it's a neural network model, a deep learning model, which deals with sequences. And the idea here is, can we bring in the notion of persistence, meaning can you remember a little of past while taking decisions on the present, right? When I am uttering the words in a sentence, the word that I produce at this moment depends on the words that I've used in the past. And my current word should have the association or the connect with the previous context, right? So making persistence as an important aspect while dealing with sequences is what recurrent neural network does. Main idea is to make use of sequential information, right? And vanilla neural networks, say for example, the feed-forward neural network that you have seen in the past, say in the case of a digit classification problem, you presume that you have got all the data, handwritten digits in the case of an MNIST data set, and the corresponding labels are available. Your problem reduces to, so you've got the entire input-output pairs are available, you build the model, and given a new input, you should be able to give the corresponding output. But that may not be very realistic in the case of a sequential data processing context. All right. And we may have to do the same task for every element of a sequence. Say when I am producing the current word in a sentence, I will use the previous context, and that's true for the next word also. Next word, I need to accommodate the current context also so that the next word comes in. All right. Which is true for any sequence processing task. If you're looking at what we call streams of data in a social media context, you may be looking at the people's sentiment or an issue, and you may have to accommodate whatever things that you've seen in the past. Basically, you have to have a persistence of the context. You have to have a memory of the context, so that at the current instance, using the available context, the history, primarily like the persistence of the history, the abstraction that you maintain about the history or the persistence, along with the current context to take a decision. And that's what neural network, RNN, recurrent neural networks are capable of, right? RNNs, we can see RNN are networks, recurrent neural networks are networks which do have a memory of the past, primarily can maintain a history. And recurrent stands for, does the same job for every other new context, right? It uses the history along with the current input to take a decision on the current context, right? Hence the name recurrent neural networks. This is the typical architecture of a recurrent neural network. So this is your input. The input can be what you call the words in a sentence, right? And it do have some hidden states. So there are multiple what you call weights connecting the hidden state input, and there is an output. So the input is connected to the hidden state through a weight matrix U, and the hidden state whatever is connected back to itself using a weight W, all right? W, and the output is produced from the hidden state through a weight V. So ST and ST minus 1, these are the what we call, these are capturing the abstractions, capturing the memory, and delay is essentially like, so at any moment when you are processing XT, you know, like the network will have memory of till T minus 1. That memory is being captured by ST, the state till t minus 1 is st minus 1. And what happens is with st minus 1 and xt, the hidden units can get updated, can get updated. And then based on that, we can essentially, through V, we can compute an output OT. At the same time, the state can also be copied, primarily like can be maintained. So basically, like st minus 1 along with xt, the current input will decide st, the new state, right? State get updated by absorbing more and more inputs. That's what's happening. So this is where the memory part of the recurrent neural network comes in, and this runs over time. So I may have a sentence to be presented. I present the first word. I update the state, and the corresponding output may or may not be produced. And then basically I'll present the next word, and things will happen like this. And so the context will have context st minus 1 have context of two words, and so the third word is given as input and corresponding, and ultimately the output may be after seeing all the words, you may say, okay, the output is positive, the sentence is a positive sentence. Or I'm talking in English, and the sequence is basically the English words that utter to make a sentence, and at any moment after a little delay, this can output a Hindi sentence. So this is a English translation context. It's called a sequence to sequence context, basically English to Hindi translation. So the input is an English sentence, which is a sequence. The output can also be a sentence, which is the Hindi sentence, right? So and the input can be a picture. The output can be a description of the picture. Input can be a video. The output can be a description or tagging of the video. Right? These are the kind of contexts that RNNs are being used. We'll see some examples. All right. So RNN, what happens here is the network input at any point in time. So the activation that goes into this layer at any point in time will be, I told you, there's a weight that connects input to the hidden node, which is U. So U dot xt, U matrix dot xt will be the contribution from the input. And you also consider the past, which is st minus 1 through a w, right? You weight by w. So u dot xt plus w dot st minus 1, basically u into xt plus w st minus 1 will be the activation that goes in, right? That will be the activation at any moment to the hidden layer, right? So st is produced out of it. St will come out of this, right? St will be like this. So basically, this is the linearity part of the network. U into xt plus w into st minus 1 will be the linearity part of the network. Then there will be a non-linearity. There will be a activation, right? So the activation function for the hidden layer is, let's label that as f of h. So f of h of u into xt plus w into st minus 1 will be st, will come out here. And that st goes through a v into st will become ot, and st will become the next state, right? St is f of that, the activation function of the hidden layer of aht, which is nothing but the linear combination of the input and the previous state, right? Network output will be P0t will be P of st. We have already seen that. P of st will be O of t, right? O of t, all right? And then the output of the network at any moment is basically, that's basically, so basically like you can presume the non-linearity out here. So basically you get the activation over here. V of st will be the output activation. The output activation goes through what we call the non-linearity here to produce output. So essentially, V of st will not be OT, rather V of st will typically go through an activation to produce OT, right? So there are two activations, one over here and one over here. This is the function f of h, fh, and this function is fo, right? The activation at output layer. That's what it is. So this is the basic operation of a RNN recurrent neural network. So this is the structure, and the way in which it operates is this input and the previous state that multiplied by the corresponding weights goes through an activation, produce the updated state. The state goes through a weight V to produce an activation over here, and that goes through a non-linearity to produce the what you call output, right? And ST will be what you call the activation over here, goes through the hidden layer activation function to become the state, the updated state. So that's what you see here. So this is straightforward, it's good. And let us expand this over time and fold it over time. So this is my network, right? U into XT goes through activation to produce a state, right, in the hidden layer, and that state goes through V and an activation to produce an output. And there's a W which connects back the state, primarily like connecting back to the hidden, which is essentially right. It's all about the memory. And if you look at the network, this is the diagram that you will typically see in textbooks. Don't think that these are multiple layers of the network. These are essentially unfolded, the same network unfolded over time. So which means that it's a recurrence, meaning the same set of weights get updated. This is the network, right? W at xt minus 1 produces st minus 1 and corresponding out t minus 1. Time t, the same UW V get what you call updated and goes through the same procedure. Basically, like this is how it works, right? The same U, W, and V get used, and this is unfolding of the network over time because we are dealing with sequences. The sequence is xt minus 1, xt plus 1. So it runs from x0 to an xn. And this is just an unfolding of the network of this particular network over time. All right. If you look at it, the vanilla meaning the base form of the recurrent neural network can be viewed like this. All right, you have an xt, right, and then there is this hidden part. Hidden part is basically like the memory. Right, you have instead of st minus 1, you represent that as ht minus 1, the same thing. ht and xt minus 1 goes through the corresponding w's and produces an ht. Right. So W is essentially, ST is essentially like, this is what the RNN cell, this is how the history, primarily like the context of an RNN cell get updated. So it goes through a W and XT minus 1 is taken, and then let's assume that the nonlinearity that they take into consideration is tan H, which runs between minus 1 and plus 1. So this is the activation function W into XT. HT minus 1 is multiplied with W, goes to nonlinearity tan H to produce HT. This is how the vanilla or the basic form of RNN memory works. Right? If you look at the unfolding part, so you have x1, x2, x3 over here, 3 inputs. Then x1 is what you call presented. The corresponding hidden is represented as h1, and the y1 is the corresponding output. Then there is a loss which can compute it's a difference between what you call the GT is essentially like the network produced at any time t. That's what GT. That's basically a notation, and so the difference is basically the cost. And yt is f of ht. F of ht is basically like this particular goes through an activation and produces ht. And HT is essentially the memory, right? HT is tan H of WXT minus 1. So it's another representation of the same thing. So what happens is you present X1 and you have starting point X0 of the memory, and then you produce H1. Then you present H2, H1 and X2 being used to produce H2, and likewise it continues, and then H2 goes to S3. H2, when X3 is presented, H2 is the previous memory, and that goes through that set of what you call computations to produce the state, the output, and the loss, the cost. That's all. That's all being represented over here. Just another representation. All right. So this is what is the forward pass. Basically, like you go from the state moves from H1 to H2 to H3 by pushing inputs H1, X1, X2, and X3, and state is basically like the previous state is being used. So you have the corresponding. So what I've just seen here is nothing but the forward pass in a network. Right? If you want to train this network using gradient descent procedure. What do you do now? You need to like kind of take the gradient of this with respect to the corresponding parameters. It's basically W. Let us look at it. So this is the vanilla, what do you call vanilla or the basic form of RNN unfolded through time. This is what is happening. This is called the forward pass, right? Let's use backpropagation. All right. What is backpropagation? This is basically the gradient update. They call it stochastic gradient update because you can randomly take points and update it. Randomly, a random set of points will be taken and the weight will be updated based on those random set of points. That's called a stochastic gradient descent update. So let's look at the gradient descent update. So gradient descent is W, the old W minus eta into dou C by dou W, right? Dou L by dou W. That's what is the gradient descent. That's what you've seen. You have seen it multiple places. Right, dou C by dou W will be, what is dou C by dou W? Dou C by dou W, C is defined in terms of the corresponding Y. All right, dou C by dou W can be written as dou C by dou Y into dou Y by W because Y is the intermediate variable. All right, dou C by dou W can be written as dou C by dou Y into dou Y by dou W. That's what is happening. So if you have, this is a single layer context. If you have multiple layers, meaning if you have multiple inputs being present, it's basically the network is going through multiple layers. Then what is happening is so y1 is f1, x1, w1, y2 will be y2. So basically, like this is a single simple context, right? If you have multiple layers, this is what is happening. So y1 goes and feeds to a w2 and then produces y2. So y1 is f of x goes through and produces y1 through w1. All right, and corresponding nonlinearity f1. So y1 goes through w2, and so y1 dot w2 goes through the nonlinearity f2 to produce y2. So C will be like like the y2, the output produced by the network and the actual y2. So you need to compute dou C by. So in order to update w2, you need to compute dou C by dou w2. You have seen that in the case of backpropagation algorithm, and you have to compute. To update what we call W1, you need to compute dou C by dou W, and this will be the update formula, the gradient descent update formula. Right. So here, what you do is you will, in order to compute this, you have to use the chain rule of differentiation. We have seen that in the case of feed-forward neural network. So the same context, y1 goes through w1 nonlinearity f1 to produce y2, and y2. X1 goes through nonlinear and goes through x1 x or x1 or x goes through a linearity w1 and a nonlinearity f1 to produce y1. Y1 goes through linearity w1 defined by w2 and nonlinearity defined by f2 to produce y2. Right, this is the same thing that we have seen earlier. Right, so this is the equation that we have seen. To find dou C by dou W1, dou C by dou W2, this is what we are trying to do. How dou C by dou W2 will be? Dou C by dou W2 will be dou C by dou Y2 into dou Y2 by dou W. Right? So which is straightforward because Y2 is directly here. Right? But if you want to compute dou C by dou W1, what happens is dou C by dou W1 will be W1. But basically C is defined in terms of y2, which means that you need to dou C by dou y1 by dou w1 that you need to, right? But since C is defined in terms of y2, so you will end up in the chain rule, which is basically you need to differentiate C with respect to y2 first, dou C by dou y2, then dou y2 by dou y1 and dou y1 by dou w. So this will be the chain rule. So there will be an application of chain rule if you have to update the weights, what you call down the network. Primarily, like when you're moving from the output layer to the input layer, you will apply chain rule of differentiation, which you have seen in the backpropagation algorithm. So all you need to do here is cost with respect to outcome with respect to previous outcome, and likewise, right? So here, and in the case of what you call in the case of recurrent neural networks, you have seen the notion of a hidden or a state. So you will have in between when you expand this, you will see like y by h, dou y by dou h, and things like that, and dou c by dou h, etc., etc. So essentially, what I'm showing here is if you have to, this is a two-layered what you call symbol network, right? When people wanted to train networks of this kind, basically a recurrent neural network, which is see, I told you this particular diagram is nothing but unfolding over time. So I can keep presenting one input at a time, corresponding output, and keep doing all this. I can keep present the entire sequence. If your input is a sentence, I can present the entire sentence, and I know I'm looking at the sentiment, meaning I have the outcome also. So which means that after presenting the entire word by word, the entire sentence word by word, the network goes through time, and then there is an output, and I know like the error, corresponding error. So if I have to, so my network unfolded look like this. So essentially, which is essentially like it looks like it's a multi-layered network. Essentially, I mean, in fact, it's not a multi-layered network; it's a single-layer network unfolded over time. But backpropagation, if we have a the structure of the unfolded form looks like a multi-layer network. And in the case of multi-layer network, we know like we can if you know the output, the system provided, the machine provided output, and the teacher provided output, you can use gradient descent procedure to compute the weights back. All right, which means that we can also use what you call the backpropagation algorithm, which is used for multi-layer network to train a recurrent neural network, which is unfolded over time. That's what I want to say. See, and that was the original idea. People came up with this idea of backpropagation through time. People said, yes, see, if you are unfolding a recurrent neural network over time, which is equivalent to a multi-layer network, why can't we use backpropagation? Instead of backpropagation happening through what you call the layers of a network, we also have layers, but layers are defined over time, right? It's a temporarily unfolded network. So let us use backpropagation through time to train what we call recurrent neural networks. That was the original thought, right? The unfolded network is equivalent to a multi-layer network. Let us use what we call backpropagation. But here, instead of backpropagation happening through layers, backpropagation is happening through time, because your multi-layer network is essentially an unfolded network over time. Right? That's what it is. Let's see, and they call it backpropagation through time algorithm. That is the original thought. Right? So this is my network. I have it's actually like producing presenting one word, first word, second word, etc., etc. So it's then there are sentence presented, and probably the corresponding output is also obtained. This let's look at the context of a translation problem. This is English sentence and this is Hindi sentence, whatever, right? Treat the unfold network as one big feed-forward network and use backpropagation through time. How do you do it? How do you do this kind of unfolding? So basically, the feed forward will be, I've already told you, present the input, the words one by one at a time. The corresponding hidden states will be computed, and the hidden state will be used further to produce the next hidden state and things like that. So it happens. So the first word corresponding hidden layer is produced. The hidden state is produced. The hidden state is used along with the second word to get the next hidden state, and likewise. And there may be outputs at each of the layer. If, say, for example, the sequence problem, there will be output at every what do you call every context. Or if it's a scoring problem or a sentiment problem, output will be produced at the output at the last layer, right? So this is basically like the forward pass. You are presenting the signal, you are presenting the input, and the corresponding output is basically you're presenting the network with the input, the sentence, the input sentence. And once you have, say, for example, let's look at the case of a sentiment score. You have the output only at the last, after seeing on the entire sentence, right? This is the forward pass, right? So the forward pass, once the forward pass is there, so you have presented the entire what you call sentence, and you know like what is the output. The forward pass will look something like this. So you produce the state using the W's, and the non-linearity, which is tan h, and THT minus 1 is taken, pushed through W to get the corresponding updated state. The updated state goes through a non-linearity F to produce the output, right? If there is an output, and the loss will be like the final output at the moment T, and the teacher provided output at that. So you know the output only at the sentiment score. The entire sentence is known. You don't have sentiment score for the partial sentences, right? For the entire sentiment, for the entire sentence, you have the sentiment score. So how do you update the weights over here? You need to update the W's, right? How do you update the W's, right? You need to find the gradient of the cost with respect to the corresponding W's, right? So how do you, how do you do that? You need to, and the cost, basically, if you look at it, you can see that the cost is different in terms of the vice, right? Cost is in terms of the vice. So dou C by dou YT, dou CT by dou YT will be like, and in turn YT is dependent on HT. So you will get what you call, essentially like what you're looking for is dou C by dou W, but you know that the dou C by dou W is, so W T plus 1 would be equal to WT minus eta into dou C by dou W. That's what the gradient descent equation is all about. So dou C by dou W, you know that. So C is essentially defined in terms of Y, and what do you call, your W is essentially used in W is essentially like kind of is used to compute H. So you will have a term which will say dou C by dou H into dou H by dou W, right? Dou C by dou W can be written as dou C by dou W is equal to dou C by dou H into dou H by whatever, dou C by dou H into dou H by dou W. So essentially, and when you expand the hidden states, if you keep looking at the hidden state, you can see that each of the hidden states themselves. So you are essentially at the output dou C by dou HT, right? Dou C by dou HT is a kind of term that you will encounter, and so dou HT, and then dou HT by dou W T, the final, basically the dou W, the weight corresponding. So dou C by dou H is a term that will occur right in the beginning, row, because your W is used to define H, right? So what you going to do is, so you will get a term. The gradient will be dou C by dou W will be dou C by dou H into dou H by dou W. So dou C by dou H will be an interesting term. Dou C by dou H will be, it can be, so H, you know that H is defined, is basically like defined, uh, right, in terms of H is essentially used to define the notion of output. So dou C by dou H can be split into dou C by dou Y into dou Y by dou H. So you'll get terms of this kind. Going further, dou Y by dou H1 is what you need to compute, because H1 directly will not directly affect YT. H1 through HT minus 1 will affect. So you can see that, right? So basically, if you are looking at what do you call Y3 is not directly affected by H0 or H1. Y3 is affected by H0 or H1 through this. H0 is affected through H1 through H3, which through H2 and then through H3, right? So essentially, when you're looking at dou C by dou H1 kind of terms in that chain rule of differentiation, you will see that you will end up terms of this kind, the Y getting affected by the hidden, what do you call, the multiple layers of hidden states, right? Dou C by dou Y, this can be further expanded. So dou YT by dou H1 will depend on dou YT by dou HT into dou HT by dou HT minus 1, etc. up to dou H2 by dou H1. You can see that easily here. So you will end up in computations of this kind, all right? This is what is happening. So if you go further, right, there's an issue with this computation. So you are essentially computing the gradient of the outcome. You are essentially computing the gradient of the loss with respect to the weight, which in turn result in a lot of what do you call, lot of values getting multiplied. And think of a context where some of these values are little above what do you call, is think of a context where the values that you are producing, which are essentially differentiated, are exploding or what do you call, are coming down to zero, right? There are two contexts which can happen. See, if these values are the values which are being differentiated are very low, what will happen? So you have a small value which is getting differentiated further down the line, and all these are fractions which get multiplied again and again. So the primarily like the gradient values will there can be a context where the gradient value can essentially vanish, right? So if you have a fraction where the denominator is what do you call, is less than 1, what is going to happen is that like, I mean, it will approach, will converge to zero. I mean, say for example, I mean, as you do more and more of computations around it, that particular numerator part, the numerator part will reach to 0, which means that the value will diminish. That's one context. The other way around, basically, like we have a denominator which is basically less than 1. It's greater than 0, less than 1. So what will happen? The value of that particular fraction, basically the fraction will go up, and as the denominator approaches 0, the value will actually explode. So these contexts can happen, and these are all multiplications of these values, which means that so some of these values can either become, depending on the numerator and the denominator, some of the values can essentially become can either approach infinity or can become 0. All right, and then these problems are identified in the case of gradient computations in a deep layered recurrent recurrent networks, meaning recurrent networks where there is the unfolding happens over large sequences. If the sequence size is pretty large, the gradients can essentially right, if the gradient computation can either diminish to 0, which is called a vanishing gradient problem, or the gradients can explode to very large values, even to infinity, which is called an exploding gradient problem. And how do you solve this problem? Is a primary question that people ask when they try to implement what you call gradient-based computation for the updates of weights in a feed in a recurrent neural networks which is unfolded in time, and especially for sequences having very large length. Right, so they call the problem, right? A product of k real numbers can shrink to 0 or explode to infinity. It's basically because it depends on whether your numerator and denominator is less than or what you call it's below 1. Right, I've told you the context where they will diminish to 0 or it will go to infinity. Right, exploding gradient problem, if the gradient value, basically like if a value of a gradient is exploding, solving that is an easy job, because if a value is increasing like anything, what you can do is you can clip the value. You can say, okay, the maximum value of the gradient is this. Right, you can do a gradient clipping or non-clipping. Right, you can actually do a gradient clipping, say like the maximum value allowed is any value beyond this will be set to this value. So exploding gradient problem is an easy problem to solve, but vanishing gradient problem, they said, it's not very straightforward, primarily because you have a lot of computations of this kind, which is essentially, it's a multiplicative operation. It's a multiplicative operation, and what you call, the moment we have smaller and smaller fractions getting multiplied, right, there are two aspects to it. Basically, like what you call the numerator value is low, and so many such numerator values are getting multiplied, and the product will approach 0. This is one context. So how do you solve this problem? It's a problem that they face, the recurrent neural network community faced when they try to use backpropagation through time to do a recurrent neural network. Right, and this is essentially happening. The vanishing gradient problem and the exploding gradient problem, you can do a gradient clipping, no worries, you can bound the value. But in the case of a vanishing gradient problem, where because of the multiplication happening over fractions, you can see that your what you call the multiplication is essentially adding what you call to the, because you're adding a number, we are multiplying a number which is less than 1. So basically, the value can easily go to, and when it approaches very low value of the fraction value, what happens is like the gradient computation can over large sequences, long sequences, the gradient can vanish. So, and it's primarily a problem with the primarily a problem because of the multiplication factor involved. Because see, like 1 by 2 is 1 by 4. Right? So essentially, like the value keeps going down as you multiply more and more values, which is less than more fractions get multiplied. It will actually like can result in vanishing the gradient. Right? How do you address this problem? Is a question they asked, and they looked at this equation carefully. Right? This is what you do. So dou C by dou H1 is dou C by dou IT into. This is something that you've already shown, and you have seen this. Right? If you look at this, if you carefully look at this computation, what you have is most of this computation, like see, your YT is affected by HT. That's good. But HT is affected by HT minus 1. So you have a lot of computations of this kind. the state, what do you call, getting different, a state at t getting differentiated with respect to the state at t minus 1. This is the kind of computation. Can you do something around this? All right. If I can make ht as a summation instead of the gradient becoming what do you call a product of a large sequence of state to previous state partial differentials. Rather, if the state is basically like is updated by adding a what you call adding an f of a function of x to the previous state, right? Suppose that instead of a matrix multiplication, right? If instead of the multiplication over here, rather if we have an update formula for the state as so in the previous thing, if you look at it, so ht is essentially so there is a multiplication there is a matrix multiplication followed by a nonlinearity. Rather, if this what do you call the update formula can be written something like this, right? If the form of that update formula instead of a multiplication followed by matrix multiplication followed by nonlinearity, and that's why you get the gradient computation as like this, right? Instead of this, can I get a form like this? Say the state at ht is updated from ht minus 1 by adding a function of x at that moment, right? So if that is the case, you can easily see that dou ht by dou ht minus 1 is constant. All right, it's essentially, I mean, your computations are of this kind, dou ht by dou ht minus 1, which essentially says that all these terms will reduce to 1. All right, so your multiplication, your what do you call that gradient computation will not have those long sequence of multiplications. Instead, you have terms of this kind, dou c by dou it, dou it by dou ht, and it ends there. Anything beyond st to st minus 1, dou st by dou st minus 1 will become 1. If this kind of form can be enforced over the state updates, right? Current state update is st is linearity followed by non-linearity. Instead of this, we need a form like this, right? So this approach, right? Instead of this, can we make this? This is called this particular approach is called a constant error flow approach, or it's also called a constant. And there are proofs around this. And I've given you in the slides. You can look at it. This particular approach of constant error flow, where instead of the what we call the update formula for the state as a linearity followed by non-linearity, basically a matrix multiplication followed by a non-linearity. If we have what we call an identity relationship between the states, right, the differential of a state with respect to its previous state will be 1, which means that all these terms will go to 1. So this is more of a constant error flow, meaning even if you have a lot of hidden states, the error flow is not going to get affected, right? And this particular approach is called a constant error carousel or CEC approach, or constant error flow approach. And this idea being leveraged to build a basic neuronal model where instead of something like this, can you build an update, the state update, or can we build the memory update? State update is nothing but memory update. The memory update, can the memory update in a cell of the RNN be in this form? And this led to the development of 2 successful models of recurrent neural networks or recurrent neural network algorithms. These are called LSTM and GRE. All right. So LSTM stands for long short-term memory, and GRE is gated recurrent unit. All right. And both these are essentially implementations of this idea. Right. Basically, the state update has to be through an identity relationship. All right. Meaning, what you call the update, the partial differential of a state with respect to its previous state should be 1. That's what it is. All right. And the key idea to do here is you need to define the basic memory cell, the basic unit of the basic memory concept of recurrent neural network needs to be redefined, and they redefined the LSTM and the GRE people. So you can look at the paper of LSTM here. LSTM and GRU, the people the researchers who came up with this idea redefined that using the constant error flow model or the constant error carousel model. It is essentially the update formula instead of matrix multiplication by and a nonlinearity. They have come out with a what we call identity relationship between the updates of the memory and that's LSTM and GRU. And so their key contribution is they redefined the basic memory cell of or the basic cell or basic neuron of a recurrent neural network. Right? Instead of computing new state as a matrix product with the old state, it rather computes the difference between them. That's what it is. You have an update formula. It's actually a summation done in multiplication. Right? The LSTM idea is explained over here, which is very straightforward. You have the current input and the previous state. It goes through a W, and then this is what they call that the memory cell. They call the basically the memory. Right? C is called the cell state memory. They call the cell state memory. So they update the cell state memory. They maintain the cell state memory. This is called the constant what we call error carousel model. The current state will be the previous state plus there's an update formula plus no multiplication plus tan h of xt minus 1. Essentially, like they maintain a constant. They maintain a constant what do you call it? Constant memory, which is essentially through an update. Right? We have an update formula like this. This is a function of x. So essentially, you're adding it up instead of a multiplication. Ht is basically the multiplication. So and ht will be the basically like if you ht will be tan. So you produce ht using a nonlinearity over here. So ht of tan and basically like you take the cell state, put it through a nonlinearity to produce ht. So you take ht minus 1, put it through a w and a nonlinearity, and that is added to the previous state. Basically, this is the difference. Right? This is basically like you have a summation over here. Right? So CT, dou CT by dou CT minus 1 will be 1. That's what it is. That's what it is. All right. And HT will be tan of CT. You carefully look at it. It will take a little time to understand. So do you just add it up? No. They say like let us not simply add it up. Add the previous state. Add a function of x to the previous state to produce a new state. Or rather, let us put it through what is called gating mechanism. Gating is essentially, I don't have to remember everything from the previous state. I don't have to accept everything that comes in my way, and I should have a mechanism to produce what I need to produce as output. So basically, they have introduced what is called an input gate, a forget gate, and a output gate. That's what it is. So input gate is basically, I told you in the initial phase. So basically CT minus 1 is CT minus 1 plus a summation. They said, hey, let us not keep everything here. Let's not keep everything in the previous state, in the current state. Let me select only the interesting part. So let me push this through a forget gate. This is my input. Let me push these things through what is called an input gate, because this is how my input is affecting my state. Let me push this through an input gate, and let's not directly take a nonlinearity of the state and produce output. Let's push it through an output gate. That's what is happening here. So CT minus 1, essentially, they said, okay, let me push through an input gate. Input gate is a point-wise multiplication. Point-wise multiplication is, say, if you have a vector of values, and I have another vector of values, which is vector of zeros and ones. Right? I have an x. I've got an I vector, an input vector, where input vector values are zeros and ones. So if I take the x vector dot I vector, only those dimensions where my I vector is 1 will be selected to the next. Right? If I do a point-wise multiplication. If I do a point-wise multiplication, is essentially a point-by-point multiplication. First position in the first position, second position in the second position, third in the third, fourth in the fourth, etc. So x through a 1 0 vector, only where there is 1, that x will remain. Otherwise, that the corresponding value will be 0. So that's what's happening here. So we'll have this particular thing is actually through a sigmoid. We'll produce a vector of zeros and ones over here, and this input, this basically like this is through the input. So this input basically the input, the actual input which is pushed through is a function of input, which is pushed through a vector of zeros and ones through a point-wise multiplication to update the thing. So basically this is called the input gate. And input gate is defined as, input gate is, if you look at it, the input gate is defined as W is through a corresponding weight vector Wi, and X, it's a function of what you call the input. It's essentially like kind of how the input gate essentially decides how close HT and XT and HT minus 1 are. If they are pretty close, they say like, hey, there's nothing much to be updated, or those dimensions you can potentially ignore. Otherwise, you add it up. So basically, like it'll give me a 0. I mean, it'll be a sigma of the activation function over here will be sigma, which means that I'll get a value either 0 or 1. That's what it is. And those dimensions which needs to be updated will have a 1. Those dimensions which doesn't have to be updated will give me a 0. So we can presume this as what we call sums of a distance measure between these two, and corresponding ones and zeros will be produced over here. And that will be pointwise multiplied by the actual what we call this particular non-linearity, which is essentially like it will give me a number between -1 and 1. So that pointwise multiplier, and that goes as the update for the cell. All right. And then there is the output. Output cell is essentially like, do you just take the state and output everything? No. Let's put it through a sigmoid. Basically, like this is called an output cell. So the what comes out of this particular computation is essentially like based on the input and the previous state, you will decide, right, what needs to be outputted. All right, what needs to be output from the current state. So that's what's happening here, and this is so the corresponding output weights are here. So I don't. So yeah, there's a mistake over here. It's actually this is OT will be OT is equal to summation WO HT minus 1 BO. So this particular equation is wrong. It's O instead of this I, this is O sigma WO HT minus 1 BO. That's what the output is. Then there is one more term here called forget gate. All right. Forget gate is essentially like I told you. So you have CT minus 1. Do you remember everything in CT minus 1? Rather, I don't have to. I can actually like allow only certain things to go through, right? And let me not add everything of CT minus 1. Let me take only certain parts. So essentially, again, it's a sigma. Sigma is the sigmoid. It's a sigmoid of what we call forget gate of HT minus 1 plus BF. So basically, like I do get a pointwise multiplication over here, and then I allow only certain things to remember. So if you look at this equation, the end result is basically like you through a forget gate you control your previous state and what goes into the current state from the previous state. Through an input gate you control what goes into the input to the current state, and through the output gate you control what goes out as output from the state. That's what it is. And this model, if you look at it, this is a summation. So FCT, you will have when you have a lot of cells of this kind connected, what is going to happen is dou CT by dou CT minus 1 is essentially the kind of computation that we end up. It'll be a what do you call it? I mean, it'll be a constant term. Right? That's essentially the point. So recurrent neural networks will find many applications, including some applications like an image labeling problem. So this is a dog, this is a human, one-to-one relationship. Image captioning problems, for example, a one-to-many relationship. So basically, there's an image, and say like there's an image of a cattle feeding in a grassland. All right, a sentiment analysis problem. You give a sentence, you give a score, get a score. Many. All right. Multiple machine translation. This is an English sentence, and this is right. This is a Hindi sentence, many to many. All right. Video labeling problem. This is a fixed size, what you call frames, and then you get what you call the corresponding descriptions of the frames. Basically, video labeling problem. Right. This is an example. So let's look at a particular example called a sentiment classification problem. Classify a restaurant review as positive or negative. It can even be a score. Right. We can have multiple words in the sentence, and you can output. There's an example for things of this kind. So basically, you have a set of inputs and one outcome, right? The segment classification. So basically, like you give the entire sentence, and then what you call, you have multiple states out there, and summation of the states will produce what you call an up or down, right? Basically, this is the kind of context. So essentially, like only after seeing the entire sentence, you'll be able to give the prediction. Right? That's what a sentiment. So this is an example where you can combine a CNN and RNN. Basically, use the problem is an image captioning problem. So, for example, the dog is hiding. A dog is hiding, right? The input is an image, and output should be multiple words, right? So, image caption problem. The architecture will be something like this. You may have a CNN capturing the features of an image, and then that will become the input to an RNN, and then RNN will have what you call the corresponding labels being available, and RNN being trained over that sequence, and then you essentially produce, right? So the output can be something else. This is just to give you an, don't worry too much about this second part of the problem, because I just wanted to show you that you can actually combine RNN and payments to make interesting applications. Two dogs are playing in the class, so use combination of RNN and CNNs. Right, summary, RNNs allows processing of variable and inputs output by maintaining state information across time steps. Backpropagation through time was interesting, but because of that multiplication factor involved in the gradient computation, gradient can either can either explode or vanish. Exploding gradient problem can be solved by using gradient clipping, but the other way around. Basically, diminishing gradient, you needed a better structure for the basic cell, and that resulted in LSTMs and GRUs. Right, and let's see an example, and then I'll potentially stop the class now for the time being. Let's see an example. I've got one lab quiz which I'm going to, which is a what do you call it? It's a sentiment classification from Google Colab. An example. I'm going to show you this sentiment score RNN. So basically, so just let me go to collaboratory sentiment score RNN. I'll give you the basic structure of the code, and then so I'm importing all the libraries. I'm mounting as always. I've taken some reviews from the IMDb. That is essentially IMDb is that movie database. Then the movie database, and from that I'm taking some reviews and putting a CSV. I can show you those reviews. Right. I put in my directory. I'll show you the data. It's in a directory called collab. Put in collab notebooks. I'll show you that data. That'll give you an idea of the data that I have in hand. I think I have around 110 or 100 reviews. So these are reviews, and some ratings are available. Right? This movie only gets whatever. Right? So I've got a lot of them. I think I have around 100 reviews. You can look at it. So this is my data. So my agenda is to basically, like, this is a sequence to a number prediction, right? Sequence to a number. So this is basically like I can't just, so yeah, I got 100, I got I think 100 reviews available. So I can't just read the 2 words and give you a rating. I need to, basically, like, the network has to go through this sequence of tokens, basically the sequence of words, and after seeing the entire what you call review, it should be able to, like, the corresponding predictions are available. So basically, it's a sequence prediction problem. So context is important. While reading Amazed, I should know that it's talking about a movie. While reading KLA TV, you should know, like, maybe it's talking about a film saw in a TV. I'm talking about Friends, I should know that it's connected to me. While talking about Elevates, it should know, like, it should talk about the previous things that stumbled across. Right. So basically, like, there's a requirement to capture the context across the paragraph or the review, and then correspondingly the outcome is available to the output. So basically, the network has to go through the steps of seeing through the review word by word, and then ultimately try to model the relationship between that sequence and the actual value. Right? That's what's happening here. And the collab notebook, what I've shown is I'm just mounting that what you call data set, and then what I do is I split into tokens. I split those things into, so basically, like, I'm trying to, so what I do now is I split into tokens. I use Stasi. Stasi is an open source library you can use. or the SPACI used SPACI to tokenize the reviews into tokens. Tokens is basically like the words out there, and then what you call added those tokens to a dictionary called lexicon. I've created a lexicon of the unique words out there. Once I've done that, I'm actually like converting what you call identifying, giving a identity to each of these words as a number. I've given index to each word. That's what it is. That's what's happening over here. Then I use word embeddings primarily. Like I use the what do you call? I mean, I find word embeddings of the words involved in the text. So yeah, I'm using essentially like kind of in this particular context. I'm reading the word embeddings, and I use pandas also in this context for computing for the word embeddings context. And then once I have that, I need to basically like I do the COW, basically like continuous bag of words embedding. I just look at the embeddings and look at that, and then to make sure that the reviews may be of variable length. So to make sure that every input is of what do you call sort of what do you call more or less equal, I do a padding. Basically, like I make sure that it's constant length, which is not very essential for the new age thing. But I do padding to make sure that we have well-formed input. Then I create the model. This is the most interesting part. I create the model. Essentially, I use Keras as always. I use Keras as in the previous example. I've got an input layer. So the layer is input layer, and the input layer is basically an embed. And it's essentially taking the embedded representation of the reviews. And the next layer is a GRU. Instead of an LSTM, I'm using a GRU layer. GRU is essentially the gradient determinant, is a basic building block of an RNN. Then once after the GRU layer, I can have multiple GRU if I want, but I have a single layer out there. And then followed by a dense layer, basically like connecting everybody, basically the decision layer. And then once I have this is basically the decision making layer, right? Which takes input from the GRU layer. And finally, like I compile the model. Essentially, I'm building the graph for the model. I build the network. Once I build the network, I basically run the model, and then I'm actually like creating the model, and then I train the what do you call the network on that particular data set, the data set I've taken, and then using the tokens out there, and then I save the model. Save the model is out there. I take the model and try to predict. I try to what do you call load the test data set, right? And test data set is also put in a padded form so that it has well-formed structure, and then try to predict. Right? That's what's happening. I'll just run the code. I'll give you the code. You can experiment the code. So don't try to what do you call mug up the code. It's all about understanding what's happening here. I just run the code and show you. Just running the code, which may require a little time, and then we'll stop there. I'll share you the code. Go back to the code, and you can use this code or maybe some other code to show you an example. Show an example while developing a class project. So it's mounted. It's basically like importing done, and so I need to give the access to my data is in the. I told you, right? My data is in the drive. So I need to give collab access to my drive. Just taking that. Give collab access to the drive. So collab should be able to mount my data now. It's available in this CSV. Yeah, mounted. So there are 200 items out there, 100 plus 100. So 200 things out there. That's the size of the thing. 100 training points and the corresponding labels there. So I'm trying to use SPACI to tokenize, convert into words. Yes, so you can see this, the what do you call it, this movie, etc. So basically, like the reviews convert to tokens. You can see the words out there, the tokens, right? Then create a lexicon around it. Yeah, lexicon is created. Basically, like 2628 what we call terms in the lexicon, the dictionary. So then you're converting, giving indexes for those words, word embeddings. You create the word embeddings for, so basically you have created a vectorial representation for each of the words. Bag of words. So basically you get the, what you call the corresponding, and then pad it, basically make sure that you have a well-formed structure. Otherwise you will end up in methods. So make sure that it's all in the same size, 100 by 189. You create the model. The model is created, and it's basically like you create the model over here. Define the model, compile and create the model here. And training, so it will take a little time. So it will take first step of this started. Training on the available token, and I'm sure like you'll not get a good model trying to predict, but we'll see that examples of it. Firefox. They're done, but the error has not come down to be 23 whatever. All right, and then models is saved model from that thing is loaded. Test data set is, let's load the test data set. Yeah, it's loaded, and then I got the padded form of it. So tokenized padded form of it. So let's look at how the test is. I think we have taken down 10 examples in the test, if I remember properly. The CSV file. I have taken some test points there. So actually, you can see that the predictions are not right actually. So got 100. I mean, I've predicted for the entire thing. So rating, the machine gave 4, and this predicted 3. So 10. The prediction RNN predicted 2, and things like that. So there are cases which are done properly. There are cases which are not done properly. So basically, all I want to say is this was just showing you building an RNN using something like a Keras, and doing it for text processing using Spassy and Pandas is not very difficult. And I want to stop recording here, and I want you to go experiment with this code. I'll be sharing this code, and this will become your next. And you can potentially reuse this code if you want to build your application there. I'll let me stop recording.